particular boundary square equals to 0 and independent of parameters, right? Independent of choices. Of parameters. Or if you want choices. We made a bunch of choices on the way. It's actually going to come out, as you've seen, this is a perturbed equation. You've got some parameter which is JT, a path of almost complex structures, a loop of almost complex structure. And if you want really another parameter, which is this perturbation, XT, coming from the Hamiltonian, from the loop of Hamiltonian functions, the result ought to be independent of these perturbations. Okay? Should be the same for all perturbations, and that's what you want. This is if you want, that's the hope, or that's what you need to check. All right. Let me go to another blackboard. I'm almost done with this. Is it visible maybe from here on? All right, so where are we? All right, that was the second idea. So you want to make this complex, and you want to really get a homology theory which is well defined independent of parameter after a lot of analytical work. And then you hope you can calculate it, right? And the third main ingredient is that it can be calculated, right? This Floer theory can be calculated. Okay? So not only can you construct it and show it's independent of choices, but you can calculate it. And the idea here, Lisa also mentioned in her talk, is that because you prove already it's independent of choices, for C1 small Hamiltonian, so I'll take like that. I believe Lisa said that for C1 small, she was doing a different flavor of Floer theory using generating functions, but the idea is really the same. The only difference was here I'm using this PDE, she was using the generating function. Did she talk about that at all or not? Yes, okay. So for C1 small Hamiltonian function H, this Floer theory is in fact the homology of the manifold. What was the name of my manifold? X. And I call the vector field also X?
Well, the vector field is XT.
So
Sometimes you called it M. On the Arnold conjecture, you called it M.
Oh, and before I used to call it X? Well, today it's called M. Okay? Today will be called M. Today the manifold will be called M, okay? So that's the ambient space we work in. So the ambient space where this flow is happening is called M. We have the flow in the manifold right now. Whatever I said before, change coordinates. Call the manifold right now. All right. So for small Hamiltonian, you can actually calculate it. It's really you're doing nothing but Morse theory with that Hamiltonian C1 small. And so therefore you are getting the usual thing, which could be a good thing or bad thing, right? It says that this Floer theory, after you work so hard to construct and show it's well defined, it's after all topological, right? So if you wanted to use it to distinguish things, it's not going to be useful, right? But in this situation, it's very useful because it's topological, because we can calculate it, and because we get something that just depends on the topology of M. Then this is the end of the proof of Arnold conjecture, and that is observing. Of course, we had a complex, and it was generated by the contractible orbits, and its homology is the same as the homology of the manifold. So obviously, the number of generators of the complex has to be bigger or equal than the number of generators for the homology. So that's how it follows. So then the number of generators, in other words, the number of what are they called? One periodic contractible orbits. Number of generators is bigger or equal than the rank. I'll just say that's A star of M. And that's really the Arnold conjecture. Because the generator, there was one generator for each one, for each contractible one periodic orbit. Okay, so that's the very, very brief outline of Floer's idea how to prove Arnold's conjecture. Do you have any questions about this? Yes?
Is this homology equivalence, is this also true for Morse homology?
Yes. This is also true for Morse homology, that if you were to do Morse homology and you start with neutral points and do gradient flow lines, at the end of the day, the homology of the complex you are getting is the homology, the actual homology, the regular homology of their manifold. Okay, so this is exactly like Morse theory. The only thing that is not exactly like Morse theory is because here we are really doing Morse theory on the loop space. You would be really expecting to get the homology of the loop space, and that's not what you're getting. You are getting the homology of the regular manifold. But except other than that, it's very much like Morse theory. Okay. All right. So that's where I think And there are many, many different versions of Floer theory nowadays, but many different flavors. So let me just say here this. So let me give you a little bit the outline. As you notice, I mean, why do I think Floer theory works the way it works? We have a very nice, simple geometric PD. It's really the holomorphic or the perturbed holomorphic map equation. And then we are looking at the space of solutions. And from the space of solutions, I mean, we're getting this differential. And from the asymptotes, we're getting this periodic, the asymptotics of the solutions are exactly going to be these periodic orbits of the flow. So everything, as I want to just show briefly, everything is coming, to some extent, these topological consequences are all coming from the study of the space of these solutions. Okay? From studying the space of solutions to this equation, we get both the periodic orbits, as I'm going to show shortly, and simultaneously we get this differential, right? And we get this complex, and we get the homology. And if we can calculate it, we can show it's independent of choices, and we can calculate it, then that's the end of the topological applications. Okay, we get a topological application of this sort. For example, existence of a periodic orbit. Okay, so let me flesh that out a little bit more. So what would you need to study the space of solutions, if you want to say a couple more words about how this machinery here works? So what are the key ingredients? Oops.
Is it lost forever now?
Hmm?
Did it fall behind the board?
Yeah, I've been losing a lot of chalk behind the board, and I'm afraid I may soon run out of chalk and I'll have to stop. So maybe, you know, it's colored. I could start writing colored chalk, but somehow I find that disturbing. But maybe you don't. But really, this is the last big piece of chalk. But it's okay. No, it's all right. It's okay. I mean,
There's more in the box.
you think so?
Yeah.
It's a commercial.
Maybe I ate it all. Maybe I dropped it all behind the blackboard or something. I don't know. It's okay. I mean,
It was
well, I guess. Anyway, all right. Back to Floer theory. Maybe this is a sign that I shouldn't, write so much on the blackboard. I should slow down. And when the quarter at Stanford is close to coming to an end, we always run out of chalk. I mean, there is never chalk in our blackboard. And I think somebody just comes and takes all the chalk. I mean, it's just saying, it's the last week of classes. You're not supposed to have any more lectures. It's supposed to just have review or something. Anyway, back to this. Think of it that way. So key ingredients. What are the key ingredients? All right. This chalk is trying to tell me something. All right. Let me see. I think I had. I don't again. So the key ingredients we are going to look again. The word comes back. The moduli space solutions to the equation star, right? Here's our equation star. And I think all the structure, all these topological consequences, and all the structure, it's really coming from the study of the moduli space of solutions. This is what I want to impress on you. Both the topological consequences about Gromov-Witten invariance. Thanks.
No excuses.
Hmm?
No excuses.
Well, I mean, while you were gone, I kept dropping pieces behind the blackboard as well, so we'll have to see. We'll have to see. All right. Let me break them in smaller pieces, so at least if I lose, I don't lose so much on the chalk. So anyway, so what I'm trying to impress on you is that really I think all these nice topological consequences are coming from the study of this amazing gadget, which is the space of solutions to this very nice equation, the holomorphic or the third holomorphic map equation. So let's look a little bit at the moduli space of solutions to this equation, right? And as before, to set it up, we need a couple of ingredients, right? One thing that I hope was, I don't know if it was so obvious, when we did the moduli space of closed holomorphic curves, we need a notion of energy. Okay, the notion of energy is crucial in controlling, in getting a compact moduli space. So there is a notion of energy here too, and the natural notion of energy in this context, you also integrate on the cylinder. Well, I guess I can call the cylinder S1 plus R, or that's what it is. But that's the domain, right? You integrate on the cylinder, and well, okay. So where is the equation? There's the equation. What you integrate is dsu squared. This should look familiar, but then there is a correction, and we're going to the other piece is going to be this: dsu squared plus dgu minus xe squared. Okay? This is the notion of energy, and if there was no Hamiltonian vector field, this would be 0, and it will be our usual notion of energy, in fact. Okay? But right now it's slightly, if you want a slightly odd notion of energy, and we really want only finite, so restrict to finite energy solutions only, right? By the way, we're working on something infinite. Before we were working on something compact, and of course the energy was finite. But here we're working on something that has asymptotic ends, and it's not obvious and it's not automatic that the solutions would have finite energy. So we're going to restrict only to finite energy solutions. In other words, this quantity is finite, and just because it has finite energy, this means that, of course, this integral has to converge as s goes to infinity or minus infinity. And just from that information, you know that any finite energy solution will have to converge to a periodic solution, because this will have to actually go to 0, okay, as s goes to plus or minus infinity. So let me say it like that. Any solution with finite energy has to converge asymptotically. Well, I'll say it like that. I'll just say it has to converge. This is a bit vague, right? But anyway, it has to converge as goes to plus minus infinity to a periodic orbit. So just because you have finite energy, it will have to converge to a periodic solution. And really what you should think of this condition, this is the condition that replaces removable singularities. I did very briefly mention it when we were talking about closed holomorphic curves, that finite energy meant you can, on a punctured thing, right? If you had a finite energy solution on a punctured Riemann surface, you can fill in the singularity and remove it. Well, that's not the case for this equation because of the presence of this pesky term. If it wasn't there, you could remove the singularity, but this pesky term prevents us from removing the singularity. But instead, the solution is going to be forced to go asymptotically to a periodic solution, which is essentially a periodic solution, the solution of x dot, I guess, equals to x t or x, I say like that, d to dt, x of t is the solution to this equation, okay? And that's exactly what we see here. Asymptotically, this u converges to x, and you get exactly the solution to that equation. All right, so that's what replaces, if you want, this replaces removable singularities. Replaces removable. All right. I still would like to save the equation. If I was to have made a much better use of the blackboard, I would have been able to save it. Yeah, I'm going to rewrite it. You can go to sleep when I rewrite the equation. So I can erase that. So this is the equation. JT at u partial tu minus xt of u equals to 0 with the asymptotic boundary conditions. Oops, I think I put them going down, right? Okay, that's the equation. Erase it. All right, so that's the next ingredient that comes in. So energy, removable singularity is replaced by asymptotic condition. So you see, what I want to point about this condition is that just knowing that you have a solution with finite energy, already you can look at its ends, and it's going to pick up the periodic orbits. You don't have to put them in; they come out sort of as a result of the fact that you have a solution to the equation. Though you cooked up your equation in such a way that you detect that. So it's not fair to say it this way.